Welcome to this mathematical detour concerning the analysis of stability of fixed points. We have seen in the previous lectures that in the phase plane, fixed points are characterized by the crossing points, the intersection points between the two null lines. And the question arises, for a given fixed point, is it stable or is it unstable? Now, this can be analyzed mathematically in a systematic fashion. All those who know how to analyze the fixed points of differential equations can skip this lecture. For those who are not at ease with stability analysis, please stay on for the next few slides. Before we go into the analysis of arbitrary nonlinear differential equations, let's look at the analysis of a linear differential equation. In our null line picture, this would correspond to a u-null line that is linear. If I search for d dt u equals 0, I find w equal a times u. That means for this fixed point here, I would have a smaller than 0. And the fixed point is chosen such that the voltage is at the fixed point 0, W at the fixed point is 0. Okay. Now, with these kind of null lines, I can do the usual picture and say, well, here I expect downward motion, leftward motion, rightward motion. I would expect upward motion here and also upward motion there. Now, if I zoom in just on this little segment, my picture looks like this. And I claim that we can find the conditions that this is stable. Stable means I start at some initial condition, and then it will zoom in to the fixed point. Now suppose now that I have a stimulus I0, which is positive. Then the null line would be shifted upwards, and it would have a new situation. Well, this is downward slope, this is left, this is right. And the old arrows are no longer valid. Well, actually, the picture looks very similar. I also have this kind of rotational component. However, we will find the conditions under which such a picture implies instability of the fixed point. If I start at this point here, the trajectory will circle outwards. It will go away from the fixed point. You can imagine yet another scenario, and in this case, it doesn't have this rotational component. Rather, in this direction, it's attracted towards the fixed point, whereas in the other direction, it's going away from the fixed point. That would be called a saddle. Now, the picture with these linear red and blue lines looks rather artificial. However, it's not, because if you just zoom in locally in a region very close to the fixed point, you will find that locally it looks like straight lines, and then this would be a stable fixed point. Whereas up here, locally, it looks like the case we had here, which is an unstable fixed point. And yet, there could also be these saddle points. That's the overview. Now, this zooming in corresponds to a mathematical operation that we will discuss now. So this is my arbitrary two-dimensional system of differential equations. The change of voltage Wu is given by some function f, which depends on the two variables u and w. And for the w variable, it also depends on the two variables, u and w. Now, at the fixed point, I will have a certain relation. At the fixed point, say a fixed point denoted at u0, w0, there is no change of d dt u. That means this right-hand side must be equal to 0. At the fixed point, there is no change of w. That means the g function at the fixed point is evaluated to 0. Now let's look close. Now let's look in the close neighborhood of the fixed point. The fixed point is at u0. X is a small distance from u0. Y is a small distance from w0. Now let's look at the change of x. I can write down a d dt x is d dt u minus u0, but u0 is a constant. So it's the same as d dt u. But d dt u is f of u and w plus r times I0. Now we said that we zoom in into the neighborhood of u0. So I can write u as u0 plus x. Okay? So I have here f of u0 plus x. This is u. Now, what about w? W is w0 plus y. So let's plug that in. w0 plus y. And I copy the rest. X is small. We stay in the neighborhood of u0. F is assumed to be a very smooth function. So we can do a Taylor expansion. The Taylor expansion gives the evaluation at u0, w0, f of u0, w0, plus df du, the first derivative, evaluated at u0, w0, times x, plus df dw, evaluated at u0, w0, times y. And then I need to add the plus r I0 over here. Now, let's look up here. We said that at the fixed point, f of u0, w0, plus r I0 adds up to 0. So this term, together with the ri0 term here, adds up to 0. So I have d dt u equals df du evaluated at u0, w0 times x plus df dw evaluated at u0, w0 times y. Now, this looks like an awkward notation, right? I write df du evaluated at, that's the vertical line, u0, w0. Let's write this shorthand notation as fu. That's the first derivative of this function f with respect to u, evaluated at the fixed point. Short-term fu. Same thing here. fw times y. So that was the Taylor expansion of this first equation. I can do a similar Taylor expansion of the second equation, and it will look very much the same. So let's do this. That's my Taylor expansion of the first equation. And from the second equation, I get this Taylor expansion, where this means the derivative of the function g with respect to u evaluated at the fixed point u0, w0, and analogously for g sub w. Now I can introduce a vector which is just x and y. And then this set of two equations becomes one single vector equation. This is the vector x, and this is a matrix of coefficients, and the coefficients arise from the Taylor expansion of the functions f and g. So we have now a linear matrix equation, and the question is whether x, that's the change, the small distance from the small distance away from the fixed point. The question is whether this x is going to increase. So if I go down to one dimension, x as a function of time, this distance x from 0 means I'm at the fixed point, I'm a little bit away. Now it could be that this distance x increases. That's the case if lambda, the real part of lambda, is positive. Or it could be that I start at this value x, but in fact, if I start a little bit away from the fixed point is at 0, I start away from the fixed point and I go back to the fixed point. That corresponds to the case that this lambda exponential approach and the real part of lambda is smaller than 0. So this is a matrix equation. Since we started with two differential equations, we are in 2 dimensions. This is a 2-dimensional matrix, and I have 2 solutions. And they are characterized by eigenvalues lambda plus and lambda minus. And if you search for this solution and you plug it into this equation, you find that the eigenvalues are related to these derivatives arising from the Taylor expansion. And we can sum up this in 2 conditions, condition A and B. Now, stability requires that the real part of both eigenvalues be negative. So it could be that the eigenvalues are real, in which case I don't need to write down real part of, but it can also be that these eigenvalues are complex numbers. Complex numbers means that lambda plus, for example, could be some real part, let's call it lambda 0, plus some imaginary part, I omega. Okay, now stability requires that both of these have negative real parts, and I can combine this with my rules here, and what I find is I find conditions on my derivatives arising from the Taylor expansions, or the entries of this matrix here, and these are the 2 conditions. Let's call this condition 1 and this here, condition 2. So if you want to check whether your system of 2 equations has a stable fixed point, you have to do a Taylor expansion around that fixed point, and you have to check the coefficients of these Taylor expansion and see that fu plus gw is smaller than 0, while this combination should be larger than 0. Okay, now we zoom in. I've started with some arbitrary 2-dimensional system. I zoom in on one fixed point, say this fixed point here. And what I find is that this fixed point here, where u is now the distance from the fixed point, this fixed point here is stable. In fact, I have a real part, lambda 0, and the rotation corresponds to an imaginary part, I omega, and lambda 0 is negative, which means we zoom into the fixed point. Any trajectory starting in the neighborhood of the fixed point will converge with some rotational component towards the fixed point. Now let's look at the next situation, at the fixed point up here. Again, this value u would be the distance from the fixed point. If you do the analysis, we find in this situation that it's unstable, and again, the structure is plus minus I omega, and the lambda 0 here is larger than 0, under the condition that this slope parameter a, that corresponds to the slope a, is larger than some critical value ac that depends on the other parameters, in particular on the time constants. In the same way, we can also analyze the third pattern, which is not here visible on the right-hand side. And in this case, I have two real parts. I have two real eigenvalues. Lambda plus is positive and lambda minus is negative. The negative eigenvalue corresponds to the attraction towards the fixed point, whereas the positive eigenvalue corresponds to the divergence of the fixed point here in the vertical direction. So we have the scenario of a stable fixed point with a rotational component, of a saddle point, and of an unstable fixed point with a rotational component. To summarize, if you have a two-dimensional system of equations, you have to go towards the fixed point, do a Taylor expansion in the neighborhood of the fixed point, look at the coefficients of the Taylor expansion, write them into a matrix, do an analysis of that matrix in terms of eigenvalues. Stability of the fixed point means that both eigenvalues have negative real parts. If you are not in two dimensions but in higher dimensions, the same type of analysis applies. Again, you have to look at the eigenvalues of the corresponding matrix. With this, I would like to close my review of stability analysis of fixed points. I hope this little review is useful for you in order to analyze the stability of the fixed points that we have for neuron models which we are interested in.